Hey guys, Jackie and I are here today. We're going to show you how to calibrate the ATI gamma sensor. It is a 6 degree of freedom sensor with analog outputs. So first we'll go ahead and show you kind of the setup and how it works. So right here we have a power supply. This is set up for 5 volts. Coming off the power supply we go into this break-in box, and then we're going to come into the analog FT box, which this is going to send power to the gamma sensor itself. And then when we get readings, those will come back to the FT box. And then coming off this, we go back into the DAC. It's a 16-bit data acquisition system. And so the first thing that we're going to do is we'll show you guys how to get the Matlab script set up and running. So the first thing you want to do is Google NI DAC MX. We'll be using this as the driver. So you can just see here on the right, you can click download and go ahead and download that and get that set up.
And then here. All right. Here's the download here.
All right, so once you have that all set up, what you're going to do is you're going to go to Matlab, and then you'll see up here in the apps, there's the analog input recorder. So go ahead and click on that. And then that will bring up this screen. And what you can do up in the top left corner, you can set the rate that you want to scan at, how long you want to scan, and the total number of scans, which is the number of data points you'll have. For this, you can just set it to 100 for 5 seconds. And then you can name your workspace variable, which is what it'll be output to. And then what you want to do is you'll want to go down here and add channels. You'll want to add 0, 1, 2, 3, 4, and 5. And then once you actually go to setup, you can click record up here at the top.
Hey guys, this is Jackie. So when you select all the channel you need here, you're gonna go here and then name your variable here, and then you're gonna hit record. When you hit record, it will record the time you want. So here we set 5 seconds here. When it's done here, you can go Matlab. So in the workspace here, there is the data you just record. So every time for each calibration axis, you're gonna record all the data all together, and you're gonna save them as a .mat file here, and then you can write a code later and to read all the data here. So let's introduce how we're gonna do this. So here is the testing rig we have for sensor calibration. Here are the pulleys on here, and the sensor is in here in the black gamma sensor, if Michael can see this. The sensor is mounted on the rail. This rod here, you can change the height. So all you need to do is unlock all the bolts here. The bolts or screw, whatever.
Yeah, it's close enough.
So when you unlock everything here, you can actually change the height for this up and down to the level you want, and then lock it later. So you gotta make sure it's locked every time before you do it. If you break the sensor, it's not gonna be happy. So, and after you change the height and everything, you gotta make sure it's level. So we have a level here. It has a magnet here. Don't use that. Don't put the magnet here on the sensor. You're gonna use this clear side here. So you gotta make sure it's level. I'm gonna do 1 axis, 2 axis, and another 45 degree. Make sure all 3 are perpendicular to the ground, and then you're good. So for the simplest calibration, the z-axis force, we have our weight here. So that's our weight box back in here. So you can put the weight in here. But one thing you should always remember is there's a maximum force that the sensor can read. For the analog gamma sensor we have, if we go to the ATI website here, so the one we have is the 32-2.51, which it can read the maximum X and Y force is 32 newtons. The Z force is 100 newton. And then the torque is 2.5 Newton meters. So do not exceed this value. If you exceed this value, you will screw the sensor real quick, and then still won't be happy. That's all it matters right now. So for z-axis, calibration, the first data you need to record is the tare data, which means there's no weights on there. So as we have that data already, then we're gonna apply load on there. So as Sid mentioned in class, when we apply load, we should apply it randomly. So not doing like 20 gram, 50 gram, 100 gram, those increase. Instead, we should do 20 gram, then 2 kilo, and go back to 50 gram maybe, and then go up to 1 kilo. So that's like a random thing. So that will be better for calibration. So have the stick here. Do not touch the weight with your fingers. It will make it less accurate here. So you get the weight here, you put it on the sensor. You see, so if we go back to the sensor analog here, you can see all the data lines here. When we leave this, all the channel reading will change. When we apply on that again, the channel reading will also change. And also, when you're doing the calibration and everything, you want to make sure there's less noise as possible. So if you're just hitting this like this, there will be a super strong vibration in the data. So you want to keep yourself and anything else away from this testing stand as much as possible during your collecting the data. So that's the z-axis here. If you want to do other axes, say x and y axis force, we have this mount here that was manufactured by Sid, or at least designed by Sid. So we have the screws that goes onto the sensor here. So the screw is M6, and gamma sensor has its maximum distance the screw can go in, which is 5 millimeter. Again, don't exceed 5 millimeter. If you exceed, they won't be happy. So we have it here. Everything's here. We want to mount it in here. You have an Allen wrench. Oh, it's bad. So screw everything in. Again, do not tight, as you're mounting the wing model before, do not tight it too much. If you over tight the sensor, it could also damage the reading as well as damage the sensor. A lot of bad things will happen. So be very careful. And this gamma sensor is different from the gamma sensor we have in the wind tunnel when we're doing the experiment. So that one has a higher reading range, but this one is again very different. So range is different. So when we mount this on there, the axis for the sensor is mounted on the side of the sensor here. So we can see the positive X, negative X, and everything. So what you need to do is, we have a 3D printed part and this mini bucket that is holding the weight in there. So the first thing we're gonna do is we're gonna change the level for the stand. We're gonna make it higher so that we can use the pulley system to apply the axial force. Very close. So we can use this pulley here for the axial force. So the bucket here, it has a fishing wire here. So you're gonna apply the fishing wire here. On the rod, there's a rod in the center here, and then on the pulley. So you gotta make sure the fishing wire is why is it's pretty tight. Pretty tight, too tight. Gotta be okay. Almost there. There we go. This is bad. So yeah, make sure the fishing wire is level so that when you apply the force is also horizontally. That's a axial force. So then we gonna lock these screws pretty tight. And then okay, there are also screws here under the gamma sensor here that's the interface. So again, you also need to make sure all the screw is tight here. So, because when you apply an axial force, if it's too big, there might be some issue. So here, okay, when it's tight, you can apply a load in there. So again, the axial force maximum is 32 newtons, so don't exceed that. The maximum weight we have is 2 kilograms, so that's 20 newton. You should be fine with that. We're gonna go with 1 kilo here. So we're gonna put the weight in this bucket here, and we're gonna make sure the force is good. And then again, we go back here, rename our file so we can do DAC2. And then we're gonna wait till again here. So the bucket might be roll a little bit. You're gonna wait till it's steady. So you're gonna wait a couple seconds until it's steady and then record the data. If it's not steady, you will have a lot of noise in your data, which you don't want. So then we're gonna record the data here. Again, 5 seconds of data. So after you record everything here, you gotta change the weight. So again, randomly, a couple different weight. So that's due to the axial force. And then we have a moment. So when we do the moment here, we need to apply the moment on both axes. So equally on each side. So if we want to do a z-axis moment, we need to add a force here and another force here, and the force is going to be the equal. So there are couple I don't know, slots on the interface here that has certain distance to the center of the sensor. So each slot stands for a moment arm. So you're gonna apply the same weight on each side and using the bucket again, and you're gonna mount the bucket fishing wire in the slot here, and then on the pulley, and make sure the wire is horizontally on the side, and the same at there. So we have the second. Where's the second? Where's the second? Ah, there we go. So the second bucket here, also with the pulley here, like this. Ta-da! So, and then you apply the weight in there. We have a scale here that we use to check the weight for the bucket here, because you also apply for the force on the bucket. So the total force will be the weight of the bucket plus the weight of your weight. So you're gonna measure the weight for both buckets. You're gonna add them into your measurement. So don't forget this part too. If you want to do the moment on the z-axis, x and y-axis, that's a little bit tricky. What we need to do is we need to lower down the mount again. So we're gonna lower it down. Gonna get rid of these two for now. Okay, so we're gonna lower this down. So as we can see here, we have 5 pulley here. The pulley in the middle, this pulley, is the one that apply the force on the z-axis. So this pulley can give you the force upward. So how you're gonna do it is you have, again, the bucket here, 2 pulley here, and then you're gonna put the pulley, the fishing wire like this, and then you're gonna mount it, the pulley here on the interface. Again, you're gonna make sure the wire is applying the force upwards like perfectly, and then you can also adjust the location for the rod, but this is very tight here. So if you cannot move it here very easily with your hand, we have another wrench here. You're gonna take the sensor off first, and then you can lose the screw on the bottom, the bolt on the bottom, and you can unlock all the stand here, and then you can adjust this to the place you want it to be, and then put it back, and then tight everything back, and then put the sensor back. So do not untight everything before you remove the sensor. If everything falls down, hit on the sensor, it could probably broke that. So again, Sid won't be happy. So that's one axis force here. Another axis force here is the force down here. So so again, there is a slot here. This fishing wire might be too long, so we have another bucket we can use for a shorter one, but you just get an idea. Apply the bucket force on this side too. It's perpendicular down here, so you have a force here and you have a force here. That gives you the X moment arm here, so that you can do the X and Y axis calibration. So that's everything you need to know for applying the force. Again, be very careful when you're doing everything. If you have questions, you can always ask Jackie, Sid, or Neil. I don't trust Neil, but you can ask him, anyone around. Just if you're not confident in what you're doing, just stop and then ask someone in case you just broke the sensor. So when you finish all your data recording here, you can go to Matlab and you can write a code for reading all the data. So the data will be saved as a timetable here. So when you open it here, it will give you all, so the time is first here, and then you have all the voltage reading from all the analog output here. So you need to write a code and then do the curve fit, linear curve fit on your data point. So it will look like this. So the code I wrote here, when you do everything, it will give you a linear fit here. All the data point you collected, the linear fit, and then all you need to do is you need to get the slope, and then you have your calibration value, and then put everything in the matrix. That will give you all the calibrations you need. So I think that's everything for the calibration. Thank you, and thanks Neil, and special thanks to Michael and for taking the video, and have fun doing the project. Great job, great job.